they want to spread out into their each orbital first. So, if you have a p orbital, pay attention, there's a little animation coming up. If you have p orbitals, how many p orbitals are there? Riley, how many p orbitals are there?
Oh, there's 10.
No, there's 3. Could you please put your phone away so I don't take it away?
Yeah. What?
Really?
Really what?
Really what?
Why'd you say really?
Moving on. If there are 3 p orbitals, and you have 3 electrons to fill those 3 p orbitals, what are those electrons going to do? They're going to fill each orbital with an up, and it's going to look like this. The first electron is going to show up, the next electron up, the next electron up. Any additional electrons will fill, but they will have to be spin down. Since those 3 p orbitals are degenerate, meaning they're all the same energy, the electrons are going to fill each of the orbitals up, 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 and then down, down, down. They will not fill up, down, up, down, up, down. They will fill up, 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 and then down, down, down.
So basically, whenever you're going up like the degenerate orbitals, it has to go positive before the negative first.
Okay, that's the thing. We don't want to say positive and negative because electrons are negative.
Or up.
Up, down, yeah. So the words we used for we use for this and not this are up and down.
Wait, so but it's only up, 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 down, down, down. Then there's 3
Degenerate orbitals, yeah.
and but then everything else is up, down, up, down, up, down.
S's are the only ones going to be up, down.
Okay.
For instance, if you had 5 orbitals, let's say you're going to fill the 3D. How are you going to fill the 3D? Up, 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 and then down, 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 down. And by the way, this is how chemists like to draw arrows. I don't have that capability in PowerPoint, but they like to draw the arrows with a little half arrow.
Why is
I
that?
guess to keep it from looking like a box. Because if you drew full arrows next to each other, it might look like a box.
Yeah.
So to keep that from happening, they draw half arrows. Does that make sense?
Yeah, that makes sense.
I don't care how you draw them. I'm going to assume if I see 2 lines, first one's up and the second one's down. Because honestly, if you don't get that from now on. Anyway, okay, so let's write some electron configurations. Okay, before we do, the governing principle about how electrons fill is called the Aufbau Principle. The Aufbau Principle states that electrons are going to fill the lowest energy orbitals first. Okay, lowest energy orbitals first. It's like teenagers, when they go to the movies, they want to get to the best spots first. You don't be like, well, we got the whole theater. Let's sit way up there. You don't do that. You sit in the front row right next to the handicap spot so you can put your feet on the rail.
Oh yeah.
And then you fill out from that point, right? So electrons do the same thing. They want to fill the lowest energy orbitals first. Okay, here we go. The lowest energy orbitals are the S, then the P, then the D, and lastly the F. Yes?
So, in the Aufbau Principle, that means it has to go the S first before it can move on to
Yes.
So like none of them will
Correct. So if an electron has the option of a 2, if an electron has the option of a 2s or a 2p, it's going to choose a 2s.
Oh wait, why is that?
Because an s is lower in energy than a p.
Oh, and they fill it first. Okay.
Yeah. Okay. If an electron has the option of a 3s or a 3p, it's going to choose the s first. Next, shells closer to the nucleus are lower in energy than those further away. In other words, level 1 is lower than level 2, is lower than level 3, and lower than level 4, and so on. So the lowest energy orbital you can have is what?
level
1
1.
S. And the highest theoretical energy orbital would be a
7.
7F, exactly.
7F.
Yeah. So the highest energy would theoretically be a 7F, and the lowest energy is 1S. So The combination of the shell and the orbital gives you the overall energy state of that electron. So the combination of the shell and the orbital gives you the overall energy state of that electron. And here's where things get kind of cool. This is the solve to the mystery. What do you think is lower energy based on what you just know? 4s or 3d? Look at how the electrons are filling on the periodic table and that crazy anomaly we talked about. What is lower in energy, the 4s or the 3d? Why don't you talk to your neighbor? Chat about it for about 20 seconds. It's okay if you don't know now, just don't not know later. All right. Would anybody like to do echo what their neighbor told them about why the? Kenneth.
So we said that the 4s is still smaller because s has 2 electrons and d has 10, and 3 times 10 is 30, and 4 times 2 is 30.
Interesting. The rationalization is not right because we don't care about how many because they're all degenerate, they're all the same amount of energy. But that's an interesting idea. The 4s is lower in energy than the 3d. This is why, if you follow a little green dot, if I can find a little green dot. I lost a little green dot. So this is why, if you follow a little green dot to the wall, you see calcium, which is 4s, fill before scandium, which is 3d. The combination of 4s is lower in energy than 3d. Why? Because s is a lot lower than d. So you have s, p, d, f, and you have 1, 2, 3, 4, 5. The combination of 4s is lower in energy than 3d. Okay. So that's why the d orbitals all get pushed down. There's another graph. There's a little kind of on a little table here that I pulled out of the textbook. Oh, come on, there you go. So this is in an old textbook which we don't use anymore. But this shows this is S. Level 1 can only hold a 1s.
Yeah.
Okay. Level 2 can hold a 2s and a 2p. Make sense so far?
Yeah.
Okay. Level 3 can hold a 3s, a 3p, and a 3d. Level 4 can hold a 4s, a 4p, a 4d, and a 4f. But they start to overlap. And the 4s ends up being lower in energy than the 3d. And the pattern continues as you go to level 5, 6, and 7. The s will always happen right before the next d. 4s will always happen before 3d. 5s happens before 4d. 6s happens before 5d, and so on. Okay. If you get confused, just remember the blocks and just read it across the periodic table. S, P, D. All right. So here's our blocks. If the periodic table was drawn like it should be drawn, it would look like this. But this is hard to put on a piece of paper. So they tend to take the F block and say, let's put it on here. They've been doing this for a long time. There's lots of different types of periodic tables, but if you were to draw it conventionally, like we normally do, it would look like this. And let's follow along, and let's read out loud, like we do in kindergarten. Let's read out loud the orbitals as we fill them. First we fill with 1s2, and then we fill 2s2, and then we fill
2p6,
and then we fill
3s2,
and then we fill
3p6,
then we fill
4s2,
then we fill
3p10,
then we fill
4p6,
then we fill
5s2,
then we fill
4p10,
then we fill
5p6,
then we fill
6s2,
and the F gets pushed down twice because it's so high in energy. So after the 6s2, then we fill the 4f14, then we come back to 5p10 and 6p6. So the D is so high in energy, it gets pushed down 1 row. The F is so high in energy, it gets pushed down 2 rows. If you don't want to remember the F's, don't sweat it. Okay? We don't do much with F's in this year. If you go on to take advanced chemistry, you might, but we don't really do much with F's here. Questions? And we're banging on all cylinders. Okay. There we go. So that's the overall electron configuration for all the atoms we know that exist. So far. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 6p6. If you are a little confused, like, I don't remember it, that's okay, it's right up there. So if you're in the front row, you can just look up there.
Oh, wow.
Yeah. If you're in the back row, well, you can wish you were in the front row. Okay. So let's look at the electron configurations of a few atoms. So look at fluorine. I want you to find fluorine on your periodic table or on the wall and see if you can predict where its last electron is going to be. And then we will fill it. So find fluorine on the periodic table. It's hanging out between oxygen and neon, and predict what its last electron's address will be. All right. Now that you have that, this is called an orbital diagram. Okay, guys, this is important. When you get a quiz or a test question asking for an orbital diagram, what they're asking for are arrows. When they're asking for electron configurations, they're asking for numbers. So this is an orbital diagram. All right, so with a show of fingers, what's the last level that the last electron is going to be in? It's going to be in 1, 2, 3, 4, 5. With a show of fingers, what's the last level going to be? 2, 3, 2, 2, 2, 3, 3, 2. Middle, third row is having a little trouble with guessing, so it's like, okay, 2, 2, 2, okay. So we got some 2s and we got some 3s. Yeah, let's see. There's 9 electrons. 1, up, down, up, down, up, 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 down, down, and we're out of electrons. Fluorine does end in the second block, or the second energy level. Its last electron, right up there, is P5 in the second row, or second level, P5, so it's 2P5. This is the the orbital diagram. This is the electron configuration. So the electron configuration for fluorine is 1s2, 2s2, 2p5. The orbital diagram is 1s up down, 2s up down, 2p up up up, down down. I'll say that again. The electron configuration for fluorine is 1s2, 2s2, 2p5. The orbital diagram for fluorine is 1s up down, 2s up down, 2p up up up, down down. You will need to be able to do both, and you need to be able to read both. So you will need to be able to write electron configurations and orbital diagrams. You will need to be able to read electron configurations and orbital diagrams. Questions? Shall we move on? A little more complicated one coming up. Our favorite atom. Question?
Okay, so I know that it's 5, like 5 over, but then why does the 5th one not have it down, and everyone else does?
Because that would be 6. We only have, good question. So the question was, why, if it's 2p5, are there only 5 arrows? Because that's how many electrons we have. We run out of electrons after we put 3 ups and 2 downs. We're simply out of electrons. Does that make sense? Okay. Now take a look at this one. Find copper. So find copper on the periodic table. It's chilaxin between nickel and zinc. And see if you can predict what's copper's last electron. did copper go? Oh, you got it? Okay, keep it then. Keep it. All right, with a show of fingers, what level does the last electron of copper exist in? Okay, just put your hands up. Is it 1, 2, 3, 4, 5? I see 3, 3, 3, 3, 3, 3, 3. I see lots of threes, okay. So let's watch it fill. Copper has 29 electrons. Oh, by the way, the total number of electrons is the sum of these superscripts. Okay, because these represent how many electrons. So if you total up these superscripts, you should get the atomic number. Okay? Fluorine has 9, 2 plus 2 plus 5 is 9. Copper is 29, hopefully they equal 29. Here we go. Up, down, up, down, up, 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 down, 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 up, down, up, 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 down, down, down. Look at that!
Oh yeah, because 100.
Yep.
What?
Like, wait a minute! How come that one fell first?
Remember, the 4s fills before the 3d. The 4s fills before the 3d. So when it's filling, again, Hund's rule tells us that you got to fill up, up, ups first before you fill down, down, downs. And then the Aufbau Principle tells us because the 4s is lower in energy than the 3d, answer your questions, I know what it is. Because the 4s is lower in energy than the 3d, the 4s fills before the 3d. Okay. Okay? Ooh, that one brought up some acid. Okay, Ken, your question.
So you go like, so it's right here, so you go down 1, 2, 3, 4, and then you count these two and you go that way, so 1, 2, or do you just start with the D's?
No, we start with the D's. Yeah,
And
start with
it's
the D's.
9, but then 1, 2, 3, 4, 5, 6, 7, 8, 9. So it ends at 3p, so why do we even...
Yeah.
Oh, because 3D. Wait, so we don't even count that. Wait, I'm sorry.
Yeah, that is.
Okay.
Why is there 1 to 9 to 10, 11, 12, 13, 14 and a half, 15 and a half things filled in? But there's only 9.
9 electrons in the D. Each arrow represents an electron. So in the D, we have 9 electrons available to fill the 3D. The first 5 fill up, 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 up. The next 4 fill down, 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 down. And once we fill this last electron, there's nothing to pair here. We don't have enough
And
more
you fill
electrons.
those ones below because the lowest
Because they're lower
gets
energy.
filled no matter what.
But when you're doing like this part, so like that, this is supposed to appear to not matter.
It very much matters.
Like
You need to
when
do-
you're counting across.
No, if you remember that it's 4s then 3d, you're going to be okay. You can't just go, you can't just fill box, 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 box. You have to remember that 4s fills before 3d. 4s then 3d. It's just one of those things you gotta have to remember. It's one of the very few things you actually have to remember in electron configuration. Okay, guys, I need to give you a caveat here. Many of you, because you're good students, will use the internet and you will look up things, you'll do a little extra tutorial before a quiz, you'll take out YouTube and you'll be, show me electron configurations, Google, and it'll show you videos. One thing you find is something kind of interesting about copper. Copper is very, very, very special. Okay. Cody, how many electrons are in the last shell in copper? 1. Copper is very special because what will often happen, this is an exception to the rule, okay? Normally, I like to shield you from exceptions, but I have to tell you about this one because it's so common. It's a very common exception. What will often happen is this down electron will move into the 3D, and this will become 4s1 3d10. It's an exception, okay? I will never test you on an exception. I'm just telling you, copper is an exception to the rule. It's a very, very special exception to the rule. But because it is so common, you might see it out in the real big scary world. Okay, yes.
So copper is like the only kind of element, and it's a electron configuration. It can change from 4s2 and 3d9 to 4s1.
Yes, copper, silver, and gold do that.
Oh,
Copper, silver, and gold are the ones that do that.
okay.
Part of the reason that they're so stable, they're so good for making coins, is because of this thing they can do. All right, we got a minute left. Let's yeah, question.
Does this have something to do with why you're conductors though?
Yes, that too. Yep. It is a really nifty thing they can do. It is an exception to the rule. Some of you can accept the exception. Some of you are going to whine about it. I just want to prepare you for the big scary rule that's out there. Better you hear it from me than from out on the street. All right. Hey, cool. Noble gas shorthand. So that's where we're going to end. We're going to noble gas shorthand last. Any questions before I allow you to fart around as teenagers? Okay. Hey. Okay. We'll just end right there. Bye.